Welcome to Chapter 9, Hypothesis Testing. The front page are just my formulas. Let me come back to the front page when I actually need these formulas. Let me introduce hypothesis testing with this example. Situation here is McDonald's has this Monopoly game. And in this Monopoly game, they're advertising that 1 in 4 wins, which is a win rate of 25%. You and your friends play the game. You play it 530 times, and you win 112 times. What is your win rate? You played the game 530 times and you won 112 times. Your win rate is then 112 out of 530, which is roughly 21%. So McDonald's is claiming that the win rate is 25%. You actually played the game and you got a win rate of 21%. Is something wrong here? Is there an issue here? You and your friends talk it over and you decide to sue McDonald's for false advertising. You take it to court. What happens in court? I'll tell you exactly what happens in court. McDonald's is going to say this. McDonald's is going to say, look, 25% is the theoretical win rate. Just like when you flip a coin 10 times, in theory, you should have half heads, half tails. So in theory, you should have 5 heads and 5 tails. But in reality, when you flip a coin 10 times, are you always going to get 5 heads and 5 tails? No, right? When you flip a coin 10 times, sometimes you get more than 5, sometimes you get less than 5 heads. Same thing here, 25% is the theoretical win rate. If you actually play the game, some people will get more than 25% win rate and some people will get less than 25% win rate. You were just unlucky and got less. No big deal. And even more, 25% versus your 21%, we're just off by 4%, single digits. No big deal. How do you respond to that? That's a pretty good argument. You respond with what's called a hypothesis test. So let's go through the process of a hypothesis test. So every hypothesis test starts off with a null and an alternative hypothesis. The null hypothesis is denoted H0. And the alternative hypothesis is denoted H1. Let me back up a bit. There's 2 types of hypothesis tests in this chapter. One for proportions and one for mean. In this example, we're talking about win rate, which is win percentage or win proportion. And also, there's no mention of mean anywhere in this example. So this is definitely going to be a proportion question. And the null and alternative hypothesis are 2 explanations for what's going on here. So 2 explanations for why we have such a low win rate when we play this game. H0 is what McDonald's is using to explain. McDonald's is saying that, look, the win rate for the game, or win proportion for the game, is actually 25%. And you're getting a low win rate because you were just unlucky. That's McDonald's explanation. That's the H0. H1 is our explanation for what's happening. So what we're saying is that we think McDonald's is lying, that the win rate is actually less than 25%, and that's why we're getting such a low win rate when we play this game. So we're saying that the win rate is less than 25%, so less than 0.25. In general, H0 is always going to have an equal sign. H1, depending on the question, is either going to have a less than, a greater than, or a not equals. In our case here, we're saying less than 25%, so it's a less than. Let me skip part B for now and jump to part C. Part C says, find the Z or T test statistic. So this refers to the 2 formulas on the front page. If we're talking about proportions, just like in chapter 8, proportions, we're going to be using Z's. And means, we're going to use T's. So in this case, because we're talking about proportions, we're going to be using Z's. So let's go to the front page and talk about the formulas on the front page. On the front page, the first formula, Z, that's for proportion situation. The second formula with the T, that's going to be for means. And then at the bottom, these are my commands in R. The first row, P norm, Q norm, are for my Z's. Second row, PT, QT, these are going to be for my T's. Back to part C. For part C, because it's a proportional situation, we're going to be using the Z formula. The Z formula has a P hat, a P0, and an N. P hat is the proportion that we got from our sample. We played the game 530 times and we won 112 times. That's our sample. So the win proportion from our sample was 112 out of 530. And we did this already and we got 0.211. So round that to 3 decimal places. P0 is the proportion that we use in our H0. So in H0 we use a proportion of 0.25. P0 is 0.25. N is the sample size. It's usually either how many people are we talking about or how many times are we doing this experiment. We played this game 530 times. That's our sample size. And then I want to plug in P hat, P0, and N into the formula on the front page. And I'm going to do this directly in Desmos. In Desmos, I'm going to start off with a fraction. On top, it's P hat minus P0, which is 0.211 minus 0.25. 0.211 minus 0.25. On the bottom, square root, fraction, and that's just to ensure that the fraction is inside that square root. Inside the square root, up top, it's going to be P0, which is 0.25. Parentheses, 1 minus P0, which is 1 minus 0.25, close parentheses. On the bottom, it's an N is 530. Make sure what you see on Desmos looks exactly like the formula for Z. Hit enter. And we got a Z of negative 2.073. That's our Z test statistic. Negative 2.073. Part D, find a p-value. I'm going to draw my Z distribution. I'm going to put 0 in the middle. And we're going to put the Z test statistic that we found in part C on our Z distribution. Negative 2.073 should be on the left side. And for all of these problems, the picture should either be shaded to the left, shaded to the right, or two tails. This is a less than. Less thans will be shaded to the left. Greater thans will be shaded to the right, and then not equals will be two tails. And the p-value we're talking about here is really just this area. So I want to find the area to the left of a Z of negative 2.073. This is really just a Z to area problem. From my front page, Z to area for the Z situation is going to be a P norm Z. So we're going to do P norm, feed it to Z, negative 0.073, and then in R, P norm, negative 2.073. And we got 0.019. And remember the way p-norm works, you feed it a Z and it spits out the left area. The question is, are we looking for the left area here? Yes, we are looking for the left area, which means this is exactly our answer. And that's the p-value. So let's talk about what we just did here. Part C and D together are really just a X to area problem from chapter 7. Here's the formulas from chapter 7. For an X to area problem, you start off by finding the Z-score, and then you do a p-norm, which is actually exactly what we did in part C and D. In part C, we used the Z formula from the front page. But this Z formula, I claim, is just the Z-score formula. From chapter 7. In the Z-score formula, for a proportion situation, this is the mean you're supposed to use, and this is the standard deviation you're supposed to use. So if you just replace the mean with the population proportion, and you replace the standard deviation with the big square root formula, you get exactly this. Right? P hat is our x. This is the proportion we get from our data. That's our x. So really, this is just the Z-score formula from chapter 7. And even the same thing for mean. The mean one looks even more like it, right? X minus the mean, x minus the mean. On the bottom, for the mean situation, the standard deviation you're supposed to use is the population standard deviation divided by square root of n, which is exactly what you see on the bottom here. S, standard deviation, divided by square root of n. Both of these formulas are Z-score. You're really just finding the Z-score. What do you do after you find the Z-score? After you find the Z-score, you're supposed to do a p-norm, which is exactly what we did in part D. We did a p-norm to find the area. Okay, what does this 0.019 mean? What this is saying is, assuming H0 is correct, assuming H0 is true, so assuming that McDonald's is telling the truth, what happened to us, which is winning 112 out of 530 times or less, would only happen this percent of the time, so roughly 1.9%. So if McDonald's is telling the truth, if H0 is true, then what happened to us would only happen roughly 1.9% of the time, which is something pretty rare. So rare, in fact, that we're going to say that a better explanation is that H0 is wrong. To use McDonald's coin example against them, what we're saying here is that they use the example of flipping 10 coins. So what we're saying here is that this is almost the same thing as flipping 10 coins and getting all heads. Right? When you flip 10 coins, yes, it's possible to get all heads, all 10 heads. But that's such a rare event that if it does happen, maybe a better explanation is that something's wrong with the coin, that the coin maybe is not fair. So what we're saying here is that, yes, if McDonald's is telling the truth, it is possible to win only 112 times out of 530 times. Yes, it's possible. But it's so rare that maybe a better explanation is that H0 is wrong, that McDonald's is lying and not telling the truth. Okay, which brings me to part E. Saying H0 is wrong, technically what we're saying here is that we're going to reject H0. And the reason why we're rejecting H0 is because what happened to us is so rare that a better explanation is that H0 is wrong. And that's why we're rejecting H0. So what's the bar for what's considered so rare that we're going to say that H0 is wrong? The bar is this alpha, this level of significance. That's the bar for what's considered so rare that we're going to say H0 is wrong. So if the p-value is less than this bar, this alpha, then you're going to reject H0. And that's your criteria for every question. 0.019 is less than 0.05, right? 0.1 versus 0.5. So the p-value here is less than the alpha, and because of that, we're saying that it's rare enough that a better explanation is going to be that H0 is wrong. In other words, reject H0. Notice that I only use the words reject H0 and don't reject H0. So those are the only two conclusions that you're going to get from a hypothesis test. Reject H0 or don't reject H0. You never say accept H0. So even though don't reject H0 in English is the same thing as saying accept H0, you never say accept H0. So this is like in a court of law, you only end up with guilty or not guilty, right? Not guilty is not the same thing as saying innocent. And I'll give you an example. Many years ago, I got a speeding ticket. Right? I took it to court, and when I got to court, the officer who wrote the ticket didn't show up, and I was found not guilty. Now, not guilty is not the same thing as saying innocent. Not guilty just meant that on that particular day, they didn't have enough evidence to say that I was guilty, and so I was not guilty. Now, I know that's not the same thing as innocent because I was speeding, so I definitely was not innocent. So you should only say reject H0 or don't reject H0. You should not say anything else. Okay? Part F, state your conclusion as a full sentence. So this is a sentence you should write for all of these. You're going to state your level of significance. So in our case, it's alpha equals 0.05. At alpha equals 0.05, level of significance. There is or is not enough evidence. So if you're able to reject, there is enough evidence. If you don't reject, then there is not enough evidence. So there is enough evidence to conclude that, and you're just going to rewrite H1 in the form of a sentence. So this, we're saying that the proportion or the win rate is less than 0.25. Or you can get it from the sentence in the question in the problem. Right? The question is saying, is there evidence to conclude this? What's this? This is that the win rate is actually less than 25%, which is what this is saying, right? The win rate is less than 25%. So at alpha equals 0.05 level of significance, there is enough evidence to conclude that the win rate is less than 25%. All right, I'm ready to go back to part B and talk about part B. What we just did, part C and D, together is what's called the p-value approach. You find the Z or T test statistic, you use that to find a p-value, and then you use the p-value to help you decide whether to reject or don't reject. If the p-value is less than alpha, you reject. If it's not less than alpha, you don't reject. That's called the p-value approach. Now, there's another approach called the critical value approach that also helps you, tells you whether to reject or don't reject. Okay, so the critical value approach, you're going to start off with the picture. And it's going to be either shaded left, shaded right, or two tails. If it's a less than, it's always going to be shaded left. If it's greater than, it'll be shaded right. If it's not equals, it'll be two tails. Now, the area here is the alpha, the level of significance. That's the shaded area. And your job in part B is to find a critical value, which is this right here. It's either a Z star or a T star, depending on whether you're talking about proportions or means. We're talking about proportions here. This is going to be a Z star. So this is really a area to Z problem. Okay, for an area to Z problem, area to Z, for the Z situation, it's going to be a Q norm. So we're going to do Q norm. And Q norm, you feed it the left area. Left area is exactly 0.05. So we just feed it 0.05 here. Okay, Q norm 0.05. Negative 1.645. And that's a Z star. Now, how does this help us decide whether to reject or don't reject? In part B, that shaded area is called the rejection region. Okay, what we just found was this boundary. This boundary is negative 1.645. Now, after you find C, the question is, where is the test statistic? Is it in the shaded region or is it in the unshaded region? If it's in the shaded region, you reject. That's why it's called the rejection region. If it's in the unshaded region, you don't reject. This boundary is negative 1.645. Where is negative 2.073? It'll be to the left of that, right? If it's to the left of that, that will put it exactly in the shaded region, in the rejection region, which means you reject. Okay, so that's another way that you can decide whether to reject or don't reject. So I'll let you decide whether you want to do the p-value approach, which means just compare p-value with the alpha, or do the critical value approach, which is figure out whether the test statistic is in the shaded region or not in the shaded region, or do both. It's actually a good way to check. They both should tell you to do exactly the same thing. So in this case, they're both telling us to reject. So that's a good way to check. Let me say a little bit more about why the critical value approach and the p-value approach are actually telling you the same thing about whether to reject or don't reject. Remember, to reject or don't reject, we really only care about whether the p-value is less than or not less than the alpha, right? So one way to find out whether it's less than or not less than is to actually find the exact p-value. But you don't actually need to find the exact p-value. What we found in part B by finding the critical value is we found the z star that has exactly 0.05 to the left of it. If I know my z is in that shaded region, then I know the area to the left of it has to be less than 0.05. Which means that if I were to find a p-value, I know that I for sure it's going to be less than 0.05. And that's why we're rejecting. Let's run through an example all the way through. Example 2. A random sample of 50 pumpkins is obtained and the mean circumference is found to be 40.5 centimeters, with standard deviation 1.6 centimeters. Can you conclude that the mean circumference of all pumpkins is more than 40 centimeters? Use the alpha equals 0.01 level of significance. The first thing we need to decide is whether we're talking about proportions or means. I see the word mean here. Can you conclude that the mean? This is definitely going to be a mean question. And then just to remind myself, for means, I should be using t's throughout this problem. For proportions, you should be using z's. Part A, state the null and alternative hypotheses. Okay, it's always easiest for me to do H1 first. So H1 usually comes from the question. It says, can you conclude that the mean circumference of all pumpkins is more than 40? More than 40. So more than 40 would be greater than 40. And make sure we use the correct symbol here. For a proportion question, we use P for proportions. Like in example 1. For a mean question, we should be using the symbol for mean, which is mu. So mean greater than 40. Can you conclude that the mean is more than 40? H0 should be exactly like H1, except with an equal sign. So it's going to be mu equals 40. Right, that's part A. Part B. Part B, we're going to draw a picture. It's either going to be shaded left, shaded right, or two tails. This is a greater than question. It's going to be shaded to the right. For part B, the shaded area is our alpha. Our alpha here is 0.01. And that's our shaded area. And your job for part B is either to find the z star or the t star. We're talking about means here, so we're going to be finding a t star. And part B is going to be a area to t question. Area to t. Area to t for the t situation is going to be a QT left area df. So we're going to do QT left area. What's the left area of this picture? It's not 0.01. 0.01 is the shaded part, which is the right area. So I need this unshaded part to the left. To find this unshaded part, do 1 minus. So we're going to do 1 minus 0.01. And 1 minus 0.01 is 0.99, I believe. 0.99. Okay, that's the left unshaded part. That's what you feed R. So 0.99. QT has a df, so comma df. This is the same as in chapter 8. Degrees of freedom is 1 less than the sample size. Our sample size here is 50 pumpkins. 1 less would be 49. So in RQT, 0.99, comma 49. Okay, 2.405. This is a T star. Now make sure it matches your picture. So our picture was shaded to the right, so we expected a T star that was positive, and we got a T star that was positive. Now, if you got a negative T star, you did something wrong. And what you probably did wrong was you forgot to do a 1 minus on the alpha, right? So look, what do you get when you do if you forgot to do that 1 minus and you did QT 0.01, comma 49. You got negative, right? Negative 2.405. So if you see a negative 2.405, just make it positive, right? Make it positive to match the picture, because you'll get the same answer if you just did it correctly. Okay, part C. Find the Z or T test statistic. We're talking about means here, so we'll be finding the T test statistic, which means we'll be using the T formula on the front page. So front page, T formula, there's an X bar, a mu 0, an S, and an N. X bar, mu 0, an S, and an N. X bar is the mean from your sample. So from our sample, a sample of 50 pumpkins, the mean circumference is 40.5. X bar is 40.5. Mu 0 is the mean that you use in H0. So the 0 refers to H0. So look at H0 and whatever you use there, that's mu 0 or P0. H0, we use 40. It's going to be 40. S is standard deviation. Standard deviation here is 1.6. And then N is sample size. So how many people, in this case we're talking about pumpkins, how many pumpkins are we talking about here? 50. And now plug this into the T formula. So I'm going to type this in directly into Desmos. So first I'm going to start with fraction. Up top, it's going to be X bar minus mu 0. So it's going to be 40.5 minus 40. On the bottom, fraction. On top, it's going to be S, standard deviation, 1.6. On the bottom, square root N, which is 50. Okay, make sure it looks exactly like the T formula. Once it does, hit enter. And I got a T of 2.210. So that's rounded to 3 decimal places. 2.210. Now already we should be able to know whether we reject or don't reject. Okay, T star is 2.405. The question is, where is 2.210? Is it in the shaded region or is it in the unshaded region? 2.210 should be to the left of 2.405. So that will put it in the unshaded region. So already I know that I'm going to don't reject. So it's not in the rejection region, which means I know for part E, I'm going to don't reject. So let's do part D. Part D is draw your picture. Put your test statistic from part C on your picture. So 2.210 is positive, so it should be on the right side. It's either going to be shaded left, shaded right, or two tails. This is a gradient problem, so it's going to be shaded to the right. And your job for part D, the p-value, is to find that shaded area. So you're finding, this is a T to area problem. T to area. T to area for the T situation is PT, T, and then degrees of freedom. So we're going to do PT. Feed it to T, 2.210. DF, degrees of freedom, 1 less than a sample size. Our sample size was 50. 1 less than 50 is 49. So PT (2.210, comma 49), 0.984. Now pnorm and PT always spits out the left area in this step. Are we looking for the left area here? No, I'm looking for the area to the right. 0.984 is the left area, so that's the unshaded part. To get the other side, do a 1 minus. So final answer for the p-value, 1 minus 0.984, 0.016. And as a hint, we expect the p-values to be pretty small. So if you're getting an answer as big as 0.984, that's 98.4%, you probably did something wrong, which means you probably forgot the 1 minus. This is more like it, right? 0.016. Now for part E, we already said, looking at the critical value approach, that it was going to be a don't reject. But now let's do the p-value approach, which is to compare the p-value and seeing if it's less than alpha. Our p-value is 0.016. Our alpha in this problem was 0.01. Okay, if the p-value is less than alpha, you reject. If it's not less than alpha, you don't reject. 0.16 is not less than 0.1. Okay, you need to add zeros to n so that it matches the number of decimal places. So 0.1 is really 0.10. So 0.10 versus 0.16. It's not less than, so this is a don't reject. And then our sentence. State your significance level at alpha equals, it was 0.01. Level of significance, there is or is not enough evidence. Okay, if you did not reject, there is not enough evidence. To conclude that, and then state H1 as a sentence. H1 is basically saying that the mean is more than 40. Or you can get it from the question, right? So mean circumference of all pumpkins is more than 40. Mean circumference of all pumpkins is more than 40 centimeters. Before we move on, let me take a step back. So example 2 that we just did was a mean question that was shaded to the right. So I don't have an example in this lecture of a proportion question that's shaded to the right. So let's talk about what changes if this were a proportion question. If it's a proportion question, you'll be doing z's throughout the problem instead of t's. And in your H0, H1, you'll be using the symbol for proportion instead of mu. So you'll be using p's instead of mu's. In part B, because we're talking about proportions, you'll be finding a z star instead of a t star. And because you're talking about z stars, instead of qt, you'll be doing q norm. And q norm, remember, doesn't have a df, so it'll just be q norm 0.99. In part C, in the proportion question, you'll be finding z, so you'll be using the z formula instead of the t formula. In part D, since we're talking about z's, you'll be doing p norm instead of pt, and then once again, p norm doesn't have a degrees of freedom, so you'll just do p norm and whatever your z is. And then part E and F is going to be the same. Okay, so hopefully, even though I didn't do an example of a proportion that's shaded to the right, hopefully it's clear what you need to change. Example 3. A national survey reported that only 15% of college students read the newspaper daily. A researcher at CRC wants to know whether the percentage of newspaper readers among students at CRC differs from the percentage among college students in general. She surveys a simple random sample of 200 students at CRC and finds that 40 of them read a newspaper each day. Can she conclude that the proportion of students who read a newspaper daily at CRC differs from 15%? Use the alpha equals 0.03 level of significance. The first thing we need to decide is, are we talking about proportion or are we talking about mean? Can she conclude that the proportion? So this is going to be a proportion. I also don't see the word mean anywhere in the question. So definitely proportions. And then to remind myself, for proportions, I should be using z's throughout this problem. Part A, this is H0, H1. Because it's a proportion question, I should be using the correct symbol, which is P. Okay, if it's mean, you should be using mu. H1 is the easiest one for me to do first. It should come directly from the question. So can she conclude that the proportion of students who read a daily newspaper at CRC differs from 15%? Differs is not equals. 15% as a decimal is 0.15. H0 should be exactly the same except with an equals in between. Part B. Part B, find a critical value and a rejection region. I'm going to draw my picture. It's either going to be shaded left, shaded right, or two tails. Not equals is going to be two tails. And the shaded area is our alpha. So alpha here is 0.03. So left and right shaded together is 0.03. And our job is to find either the z star or the t star. We're talking about proportions, so I'm looking for the z star here. Okay, from my picture, I expect two z stars. And just to back up a bit, the reason why it's two tails is because not equals, you could be not equals either on the high side or on the low side. So that's why it's two tails. Okay, this is really a area to z problem. Area to z. Area to z for the z situation is going to be q norm, the left area. So we're going to do q norm, the left area. What's the left area of my picture? 0.03 is the left and right together. If I just want the left, divide that by 2. All right, so 0.03 divided by 2. 0.03 divided by 2 is 0.015. Okay, that's our left area, which is what our feet are. So we're going to do Q norm. Q norm doesn't have a DF, so I don't need a DF. Okay, Q norm 0.015. Negative 2.170. Okay, that's actually one of my z stars. That's the left one. So I expect the one on the right also. So the one on the right, just by symmetry, is going to be positive 2.170. And those are my two z stars. Part C, find the z or t test statistic. We're talking about proportions here, so I'm going to be using z's. My z formula from the front page has a p hat, a p0, and an n. So I need to find a p hat, a p0, and an n. Let's start with p0. P0 refers to h0. The proportion in your h0 is 0.15. That's our p0. N is our sample size. How many people are we talking about here? We're talking about surveys a simple random sample of 200 students, so 200 people total, so that's our N. P hat is the proportion from our sample, so this is going to be something over something. Our total is 200 on the bottom, so how many students read a newspaper here? 40 out of 200. Okay, 40 out of 200. 0.2. Okay, if it's a long decimal, round that to 3 decimal places if you need to. And then plug this into our formula for z, which is this z formula. So I'm going to type this directly into Desmos. Fraction, up top, p hat minus p0, so 0.2 minus 0.15 up top. On the bottom, big square root, so square root fraction, so that makes sure that the fraction is inside the square root. Inside the square root, up top, it's going to be p0, which is 0.15. Parentheses 1 minus p0, 1 minus 0.15. And then on the bottom, n, 200. Okay, make sure it looks exactly like the z formula. And we get a z of 1.980. Part D, draw your picture. Picture should look exactly like whatever you drew in part B, so it should be two tails also. Okay, because it's not equals. Now, put your z or t test statistic on the picture. 1.980 is positive, so that's the one on the right. Okay, there should also be one on the left. Okay, just by symmetry, it's going to be negative 1.980. And your job here is to find the shaded area. That's the p-value, the shaded area. This is a z to area problem. So z to area. Z to area for the z situation is going to be a p-norm. So we're going to p-norm. Now, what do you feed r? Do you feed it the positive 1.980 or do you feed it the negative 1.980? The way p-norm works, remember, is you feed it a z and it spits out the left area. Okay, so it's going to spit out the left area of whatever z you feed it. Okay, I'm not going to feed it the the positive 1.980 because it's going to find the area to the left of that 1.980, which includes this unshaded part that I don't want, right? So I'm not going to plug in the positive 1.980 because it's going to include this unshaded middle part that I don't want. So I'm going to always plug in the negative 1.980. Okay, and this is only on the two-tailed ones. So for the two-tailed ones, you always want to plug in the negative one because I do want whatever's left of that, right? So the left of negative 1.980 is this shaded part, which is part of what I want. So I'm going to plug in negative 1.980. P-norm doesn't have a df, so that's it there. So P-norm, negative 1.980, 0.024. Okay, that's not my answer yet. 0.024 is the area to the left of negative 1.980. Okay, here's negative 1.980. Area to the left is 0.024. So that's this left part here. I want the area of these two together. So by symmetry, I also know that this area is also 0.024. So my final answer, you can either add those two up or take one of them and multiply by 2. So I'll take one of them and multiply by 2. So I'll do 2 times 0.024. And that's going to be my p-value. So 2 times 0.024. 0.048. Part E, reject or don't reject. So to decide, you're going to look at your p-value and compare and see if it's less than your alpha. Our p-value from part E for part D is 0.048. Our alpha, 0.03, is 0.048 less than 0.03. 0.4 versus 0.3, that's a no. So this is a, since it's not less, this is a don't reject. And then just as a double check, let's check with the critical value, the rejection region approach. So these two boundaries are negative 2.170 and 2.170. Question is, where is 1.980? Is it in the unshaded part, or is it in the shaded part? That's negative 2.170, that's positive 2.170. Where is 1.980? 1.980 would be in the unshaded part, right? Which also tells us to don't reject. Okay, so that means that we probably did something right. Part F. State your conclusion as a full sentence at, state your significance levels at alpha equals, it was 0.03. Level of significance. So if you did not reject, there is not enough evidence to conclude that, and then state the H1 here, which is that the proportion is not 15%. Or you can get it from the sentence. Proportion of students who read a daily newspaper differs from 15%. So proportion of students who read daily differs from 15%. Example 4. The mean annual tuition and fees for a sample of 12 private colleges was 39,200 with a standard deviation of 4,300. Can you conclude that the mean tuition and fees for private colleges is different from 35,500? Use the alpha equals 0.03 level of significance. The first thing we need to decide is, are we talking about proportions or are we talking about means here? Can you conclude that the mean? So this is definitely going to be a mean question. And then to remind myself, means, I should be using t's throughout this problem. Part A, H0, H1. Right, because we're talking about means, let me use the correct mean symbol, which is mu. H1 is usually the easiest one for me to do first. It comes straight from the question. Can you conclude that the mean tuition and fees for private colleges is different from 35,500? So different, is it not equals? 35,500. H0 should be exactly the same except with an equals in between. Part B, find a critical value and sketch the rejection region. So draw the picture. It's either going to be shaded left, shaded right, or two tails. Not equals, it's always going to be two tails. Okay, the shaded area is the alpha. Our alpha here is 0.03. And you're either finding the T star or the Z star. We're talking about means here, so we're finding the T star. And this is really a area to T question. So area to T. Area to T is a, for the T situation, it's going to be a QT left area DF. So we're going to do QT. Left area of this picture. So left and right shaded together is 0.03. If I just want the left, divide that by 2. So we're going to do 0.03 divided by 2. And 0.03 divided by 2 is 0.015. Okay, that's what U feed are. Okay, QT has a DF also. So degrees of freedom, 1 less than the sample size. Sample size 12 colleges, 1 less would be 11. So we're going to do QT 0.015 comma 11. All right, so in R, QT 0.015 comma 11, negative 2. 2.491. Okay, that's a t star. From my picture, I expect two answers, right? Negative 2.491 is the one on the left. The one on the right is going to be positive 2.491. And those are my two t stars. Part C, find the ZRT test statistic. We're talking about means here, so I am looking for a t. So I'll be using the t formula on the front page. T formula has an x bar, a mu 0, an s, and an n. So x bar, mu 0, s, and an n. X bar is the mean from your sample. So from our sample, what was the mean? The mean for a sample of 12 colleges was 39,200. So x bar is 39,200. Mu 0 refers to H0, so it's the mean that you use in H0. Here's H0. The mean that we used was 35,500. S, standard deviation. Standard deviation was 4,300. And N, sample size. Sample size here was 12 colleges. Plug everything into the T formula. So in Desmos, I'll start with fraction. Up top, x bar minus mu 0, that's going to be 39,200 minus 35,500. On the bottom, another fraction. On top of the bottom fraction is going to be s, which is 4,300. And on the bottom of that one, square root n. Our n was 12. All right, 2.981. That's our t, test statistic. 2.981. Part D, draw your picture. Okay, this should be the same picture as part B, so it's going to be two tails. And put your test statistic that you found in part C on the picture. Positive 2.981, that should refer to the one on the right. So positive 2.981, which means the one on the left is going to be negative 2.981. Okay, and your job here is to find the area, the shaded area. This is going to be a T to area problem. So T to area. T to area for the T situation is going to be PT, T, and then DF. So we're going to do PT. Now, just like the previous example, I have two choices here. Do I plug in the positive 2.981 or do I plug in the negative 2.981? PT is always going to give you the area to the left of the T. I don't want to plug in the positive 2.981 because left of it includes this unshaded part that I don't want. The negative one's okay, right? Negative 2.981, I do want all of the stuff to the left of that. So I'm going to plug in the negative 2.981. So negative 2.981, comma, DF, so one less than the sample size. It's going to be 11 again. So PT in R, negative 2.981, comma 11, 0.006. Now we're not done. Okay, 0.006 is the area to the left of negative 2.981. So that's this part. Now I want the shaded area of both together. So the one on the right is also 0.006. So either add those two things up or take one of them and times it by 2. So I'll times it by 2. So my final answer for the p-value is going to be 2 times 0.006. and that's going to be 0.012. Part E, reject or don't reject. So to decide, you're going to look at your p-value and see if it's less than your alpha. P-value was 0.012. Our alpha, in this case, was 0.03. Question is 0.012 less than 0.3? Yes. This is really basically 0.1 versus 0.3. So it is less than, so you do reject. If you're having trouble, either add on a 0 to match the number of decimal places. So this is just 0.12 versus 0.30, so it's basically 12 versus 30. So definitely it's less, which means it's going to be a reject. Okay, let's double check our reject, don't reject using the critical value. So our critical value approach, the boundary here are negative 2.491 and positive 2.491. And the question is, where is 2.981? 2.981 should be to the right of this 2.491, which would put it in this right shaded area. So it is in the rejection region, which means you do reject. So it does match our p-value approach. And then finally, at alpha equals, our significance level was 0.03. There is or is not enough evidence. So because we did reject, there is enough evidence to conclude that and then restate H1 in a sentence. You can either write it from here, or it should be in the question also. Can you conclude that the mean tuition fees for private colleges is different from $35,500? So mean tuition fees for private colleges is different from $35,500. And that's hypothesis test. Have a good day. See you in the next video.